Let's imagine we have already trained our pneumonia detector model on some training data, and now it's time to evaluate the model's performance. This is where our test dataset comes in. We take a test image from the test dataset and feed our model with this image. Since this image is in the test dataset, we already know its actual label, but our model has not seen it before. Our model is going to make a prediction looking at this image, and then what we do is to compare the prediction with the actual label. If they are the same, we will say this is a correct prediction. If they are not the same, then this is a false prediction. Let's say we did this process 100 times with different images in the test dataset. The best way to understand how our model does is to put the results of these 100 test images to a grid, which is called confusion matrix. Here, in this table, columns show the predictions of our model, while the rows show the actual labels. As you can see in the screen, out of 100 test images we used, there are 50 pneumonia and 50 normal cases. Of the 50 pneumonia image, our model predicted 45 of them correctly and 5 of them incorrectly. Similarly, looking at the normal image, our model predicted 40 of them correctly as normal. For 10 images, it had mistakenly predicted as pneumonia. So let's move to the first success metric, accuracy. Accuracy is the number of correct predictions divided by total number of predictions. It's one of the most common classification metrics and one of the easiest to understand. As shown for our model, we have an accuracy of 85%. When we have balanced classes, accuracy is a proper metric. However, in some unbalanced cases, it can turn to be an inaccurate metric. For example, if we take this pneumonia detector model and implement it in a real world, it is very highly likely that we can encounter a situation where there are only 10 pneumonia cases against 990 normal cases. Imagine our model does an extremely terrible job and classifies each image into normal class. Even in this case, our model will have an accuracy of 99%. Considering the possible negative effect of this on actual pneumonia patients, this model is unacceptable even with the high accuracy. Surely we must find other metrics than this one. And this is where precision and recall steps in. Precision is the fraction of relevant instances among the retrieved instances, while recall is the fraction of the total amount of relevant instances that were actually retrieved. Confused? That's normal. Let's tell it in a simpler way. Precision is, of all the cases that we predicted as pneumonia, what percentage of them are actually pneumonia? In the grid, it is A divided by A plus C. However, recall measures what percentage of the actual pneumonia cases we correctly predicted as pneumonia. This time the formula is A divided by A plus B. Depending on your problem, you may want to maximize one another. In our pneumonia detector model, I would suggest to focus on recall, because it's mostly okay if we incorrectly say someone is pneumonia. He or she can go for further tests and the doctors will quickly realize he or she is not sick. On the contrary, if we say someone that he is healthy and send him home while he is actually sick, this person's condition can go worse and this may lead to undesired consequences. If we check again our extreme case, we will see that even though our model had 99% accuracy, its precision and recall scores will be 0%. We can train our model to maximize its recall, so instead we can get a grid like this. Our accuracy is still very high with 98%, but our recall became 100%, which means we are not missing any actually sick person. This is the key point in classification problems. You might have a problem where precision and recall might seem equally important for you. Then you can take the harmonic mean of these two values and combine them into one metric, which is called F1 score. Harmonic mean is a better solution than the simple mean, as it punishes some extreme values and always will be closer to the lower value. So, if you train your model saying it should maximize the F1 score, it will do its best to increase both precision and recall at the same time. I hope all these videos help you get an intuition about classification. Now let's move to unsupervised learning.